Let's start with the difference between slab prism and lens. What is a slab? It's like a rectangular glass block. Two surfaces, two reflecting or refracting surfaces. Transparent, and the reflecting surfaces is plain. Plain surface means flat, flat surface. And you can see the two surfaces, they are parallel. So I say here the property of a slab is two plane surface, two flat surface, and also they are parallel. Okay, that we call it a slab. Now, how about a prism? How is it different from slab? Okay, prism, it comes in many forms, right? So let's take the normal one, the triangular prism. Also transparent glass, and you can see the reflecting surface is also flat, right? So the reflecting surface is also flat. Here, here, and here. But the two reflecting surface, they are not parallel to each other. Okay, so this one is sloping, this one is sloping also, not parallel. Now, how about a lens? What is considered a lens? A lens is if the reflecting surface is not flat and also not parallel. Okay, so meaning that you have two types, right? Two types in general. You have the concave lens and the convex lens here. Two reflecting surfaces, again, left and right, and they are curving. They are not plane, okay? And also they are not parallel. Now, to consider a lens, at least one side, if it's curved, then we say it a lens. Doesn't matter the other side. At least if you have at least one side is curved, then that is a lens already. So sometimes you have a lens like this, curve one side, and then you have flat on the other side, like this. Okay, this is also a type of lens. Also a type of lens. So as long as one side is curved, we consider it a lens. So here, just to let you see in general, what are the differences between slab prism and lens. Okay, talking about lens, how do you differentiate? Very easy. Concave lens, you see the corner, if it's thick at the corner and very thin at the center, then that is a concave lens. Concave. If it's thin at the corner and thick at the center, then that is a convex lens. They have another name. Concave is a diverging, and convex is a converging. Converging is focus the light ray. So the property of convex lens is to focus light onto a point. No matter what direction that the light is coming in, they tend to focus the light ray. So if the light ray is spreading out like this, again, it decreases the spread by deflecting inward. That is also focus. Okay. Now the opposite, concave lens, diverging means spreading. It spread the light ray. So if you have a converging lens, if you have a converging light pass through the concave lens, then the converging ray will be diverged. So that is it direct the way. Okay, so that means it spread the light. Later I'll show you examples. Okay, so the basic things to know before we go to some of the important parts is that let's take the common one that often we'll ask is the convex lens. Okay, we have a convex lens here, and the line joining the center, if you measure the top bottom and you find the center here, the center of the lens, and you draw an axis, horizontal axis. This axis is very, very important. You have many axes. You can have this axis, you can have this axis, you can have this axis. All lines that pass through the center is called an axis. But the most important axis is the principal axis. This is an axis, this is an axis, but this one is the principal axis. Okay, principal axis. Right. Now, the principal axis here, because you see the lens got two curved surface, right? One curve has one center, another curve has one center. So this is curving to this side, so it has a center somewhere here. Okay, let me label it reflecting surface number 1 and reflecting surface number 2. Reflecting surface number 1 has a center over here. Then reflecting surface number 2, also it has a center, but on the other side over here. Okay, this center, we call it center of curvature. Center of curvature. Now, the center, if you measure the center to the lens, that is the radius, correct? That is the radius. Here, measured from where to where? From this center to this point to the center of the lens. So somewhere, by right, it should be here, right? Because it is this surface. Because the lens is very thin, so I would just assume that the center line is at the middle. Okay? Because the lens is very, very thin. So I would just assume that this is measured to the center. So I'm going to draw a center line across the lens like this. Okay? So any light ray that I draw, I would connect to the center of the lens, not the curved side, not the curved side, the center of the lens here. Okay, this length here is the radius, correct? From center to circumference is radius. So if you take the half of that, then you get very important point that we call it the focus. Focus. Now, the difference between capital F and small f. Capital F is the point itself. Okay, the focal point, the focus. We use capital F. If you measure the distance from the lens to the focal point, this one, it is distance, right? It is distance. So this distance, we call it the focal length. Focal length. It is a length. Okay, a physical quantity. Focus is a point. Focal length is the length, right? So the focal length, we use a symbol of lowercase f. Okay, so uppercase f is the point itself. Lowercase f means it is the length. And in most cases, you'll see that we would use the small f more often, especially when you draw the diagram. 1f, 2f, 3f, like that. Okay, so here focus. Now to focus, twice the distance of the focus, twice the distance of the focal length would be the center. So that means here, if you take the radius, you divide by 2, you get the focal length. Okay, and the same for the other side. The other curve also has a focus. So that means for one single lens, we got two focus, left and right. This is, we call it focus number 1. This is, we call focus number 2. Doesn't really have a big difference, like it's the same because the focal length is the same. And again, we have a center here. Okay. So these are the terminologies, okay, to know. Now, here, how does the light ray behave around the focal point? How does the light ray behave around the focal point? What does the focal point do? You see, here I consider a convex lens. If the light is coming parallel to my principal axis, again, I have F1, F2, okay? If the light is coming towards my lens, but parallel to the principal axis, what happened to the light ray? Parallel light ray. Now, first thing, parallel light, how do you get parallel light ray? Parallel light ray is you get from object very far away, 很远的 object, okay? 他们的 light ray 来到这边是 parallel. Because the distance is too big, you cannot really see the deflection. So I would just draw parallel rays to indicate that the object is at very, very far away, like at infinity. Can be like the sun, the moon, very far away. So the light reaching us is parallel. Okay, so parallel ray is light ray from distant object. Now, what happened to this parallel ray as it passed through the lens? Because it's transparent, right? So it can cross, not reflect. It can cross, it refracts. It refracts to the other side, and when it refracts, it will go to the focal point like this. This is what the focal point do here. Any parallel light ray pass through the lens will converge to the focal. That's why we call it converging lens. Okay, so this is the behavior of the light as it passed through the lens. Different light ray pass through different object, it behaves differently. If the light were to pass through the slab, how does it behave? You can draw, right? So if it's perpendicular, then it goes straight through. If it crosses at an angle, then there's refraction. Same for the prism. The light ray pass through the prism behaves differently than the light ray pass through the slab. And the light ray pass through the lens also behave differently when it pass through the slab and prism. So the behavior is that it crossed the focal point. Now, the same is true for the reverse. If I reverse the light ray, I change this arrow to this. Can I say this is correct also? Yes, because there is a principle that says light can be reversed. Okay, so that means these two diagrams very important to understand. The second one, the green arrow. Okay, the light appears to come from F2, right? It is coming from F2. And this is a diverging ray. Okay, let's say that the light comes from F2. This is a diverging ray. And the diverging ray pass through the lens, it becomes parallel. Okay, it becomes parallel. So the opposite is also true. So I also can draw my lens like this. Here, the first one is the first diagram here, which means that if you have a parallel light ray, it will converge to the focal point. And the second diagram, which is also true, that I can draw, if I have a light coming from F1, then this light will be parallel after passing through the lens, like this. The second one is actually the reverse of the first one. Okay, so any light ray coming, it will become parallel after passing through the lens. Actually, this one you can think of it like, without the lens, where will the light go? Without the lens, the light will go here, correct? But with the lens, it deflected towards inward. It deflects inward. Same here. Without the lens, the light would go like this. With the lens, the light is deflected inward. Deflected inward means converging. Converge. Okay, converge. Converge doesn't necessarily mean you have to focus. It just means like there's a change in path inward, like that. So remember these two diagrams. Number one, number two for a for a convex lens. Okay, now we go to concave. Let me write this here, convex lens. Okay, so for a concave lens, again, we have two focal points. F1, F2. When you have parallel incoming ray pass through the concave lens, how does it behave? Does it cross the focal point? No, because that would be convex. So instead of crossing the point, it goes diverging like that. It goes diverging. Now, and then these two rays that diverge, they appear to come from focal point number one. That means I can extend this and the light appears to diverge from focal point number 1. So focal point number 1, I can also call it as a point on the principal axis from which the light ray appears to diverge. Okay, so that is F1, the opposite of convex lens. Now, the opposite is also true. If I reverse the direction, meaning that, let me draw the second diagram. If I reverse the direction, I get something like this. One, two. So we have incoming ray. I'll just switch it to the left-hand side. Okay, this one, the incoming ray, I'll put it at the left-hand side. So you have like a converging ray like this. After passing through, where will it go? Parallel. So after passing through, parallel like this. And this one, these two rays, you can join the line, and it's like they are directing towards this point. Okay, they are directing towards this point. Any light ray that is coming, directing towards the focal, will go back parallel. This one is the reverse of this one. This 4 diagram shows the behavior of the focal point of each lens and what does each point do to the light ray. Please remember 4 of this diagram. Okay, now we go to the next one. The next one is sketching. How do you draw ray diagram? Now, let me erase this. Okay, let's do one example. We start with a convex. To sketch a ray diagram, all you need to do is just to remember 3 things. Number 1, parallel focus. Number 2, center. Number 3, focus, parallel. Only these 3, okay? Parallel focus, center, and number 3, focus parallel. Now, I'll teach you how to use this 3 to draw any light ray diagram, regardless of concave, convex. Okay? Now, follow these simple 3 rules to sketch your light ray. Now, let's say we start with convex. So you should have the focal point, right? So the focal length, I'm going to use small letter f just to show that the distance here. And normally you will see they write the center as 2f, right? 2f means twice the focal length. Whatever is the length here, you take the twice, that is the center. So 2f is the same as center. Here also, you have 2f. Now, before you sketch, make sure you label the f and 2f, and then the lens. Let's start with our object. Okay, where is our object placed? Let's say our object is placed somewhere here. This is the object over here, like that. Now, object always upright. Okay, we always start with an upright object. So it must be on top of the x-axis. Here, draw the first one, parallel focus. That means the light ray come from the tip of the object I'm going to draw a light ray coming from the tip of the object, and then it goes parallel to the principal axis all the way to the lens. Again, parallel, focus. Okay, so parallel to principal axis and then to focus, to focal point. Put the arrow like this, like this. This is ray number 1. Okay, number 2, center. This is the easiest one. From the tip, straight away through the center. The center of the lens here, not the 2F, is the center in the middle, the origin. The origin. Let me extend this one a bit. Extend this one. Okay. So this is center. Ray number 2. Number 3, focus, parallel. That means I have to go through focus first. Which focus? This one just in front of it, not the other side one. Okay, so this one just in front of it. Focus. And then all the way to the middle of the lens, then you go parallel to the axis. This, like this. This is ray number 3. All 3 rays, you see that they intersect at the same point. Light, all this light come from the object, from the tip of the object. So after refraction, they intersect at the same point. That means that location is where your image is, where your image is formed. You can use any 2 of the 3 rules to draw your ray diagram. Just pick 2. No need to draw 3. Okay, just pick 2. 2 is enough. You can either pick 1 or 2, 2 or 3, or 1 or 3, or you can just stick to 1 and 2 only. Okay, now they intersect at here, which means how do you draw your image? You see all the 3 lines, they are from the head of the arrow, right? Head of the arrow. Let's say this is point A, and the tail of the arrow is point B. AB. So all these 3 lines is coming from point A or B? From point A. So that means here is point A. I will call it A prime, okay, the image of A. Where is point B then? Point B is directly below point A here. It is on the principal axis, correct? On the principal axis. So here, same, you must direct B in a straight line, but this one is on top of A because it must be on the principal axis. Yeah, then you join a line like this, and then you draw the arrow of the image here. This, label it I image, and this is your object. A proper way to sketch a ray diagram. Your diagram must consist of at least 2 light rays, must show the image, you draw the image, just represent by arrow, and must show the type of lens and also the focal point. If you have all these 3, then you get full marks for your diagram. Also, don't forget the arrow, and please use a ruler. Use a ruler to draw your ray diagram. Okay. After we draw the ray diagram, what do we want to do? Oftentimes, you will be asked to state the characteristics of the image. Say, okay, state the characteristics of the image form. Now, think of characteristics in 3 things, only 3. Number 1, whether it is upright or inverted. Number 2, whether it is real or virtual. Number 3, whether it is magnified or diminished. okay, becomes smaller. Whenever you see characteristics, you describe according to this tree, full marks, okay, only this tree. Now, of course, sometimes you can describe magnification as well. Later we'll come to this. Magnification, meaning that the magnitude of it. For example, like if it's magnified, then how many times? 2 times magnified? 5 times? Okay, what is the magnification, magnitude of the magnification? Okay, how do we know whether it is upright or inverted? Just look at the diagram. Okay, just look at the diagram. So if it's inverted, then it's inverted. So if it's below the principal axis, then it's inverted. So this is inverted. Number 1. Real or virtual? Now, here you see, where is the eye position? On the right, right? This is the eye position. Your object is on the left. You look through the lens. You see the object through the lens. If your eye is at the same side as the object, then your lens becomes useless. Your lens becomes useless because you want to see object through the lens, right? So your eye and the object must be always opposite side. Okay, so that's the first thing. Now, how do you know whether it is real or virtual image? If the image is on the same side as the eye, then it is a real image. Use the eye for your reference. Use the eye for your reference. If the image is on the same side, let me write this down. Image on the same side as eye position. So if image is same side as the eye position, that means it's opposite to object, right? Opposite to object. Then that is a real image. This applied to all lenses. Now, we are not talking about mirror yet. Huh? You have concave and convex mirror, that one later. We are only talking about lenses. Okay, so image on the same side as the eye position, it is a real image. So here, is it real or virtual? It is a real image. This is how you identify it. Number 3, is it magnified or diminished? Again, you can see from the diagram. Here, become longer. Oftentimes, it is obvious to see. Okay, if it's not obvious, then you measure. This diagram is better to draw according to scale. Okay, so for example, if your focal length is 8 cm, you scale it, okay? You use a 1:2 ratio or a 1:3 ratio like that. So if you draw with scale, then you get the correct answer. Okay, especially when you want to measure all this. Here, unless the question only asks you to sketch. The difference between sketch and draw. Okay, draw means you have to use proper scale. Sketch means you do not need to use proper scale. They just want to see the outcome. Okay, they just want to see the things that whether you draw it correctly or not. Sketch. Draw, you have to show the scale, proper scale. Or maybe draw, they want you to measure the magnification as well. Okay, so this one is magnify. Magnify. So inverted, real, and magnify. That is my characteristics of image. Okay. Is it all the same? Is the characteristic of image the same? Always? Answer is no. It depends on where you put your object. Where is the location of the object? There are 6 locations. Okay, I extend this. Oops. I'm going to do like this. On the left hand, the region closest to the lens, the region between the F and the lens, this region here, I will call it U smaller than F. F is focal length. What is U? U is the distance of the object from the lens. Okay, that means if you look at the diagram, where is U? U is from this object to the center of the lens. This is U. Okay, it is the distance measured from the object to the lens, parallel to the principal axis. Parallel to the principal axis. So for this region would be U less than F. That means if U less than F, that means your object is somewhere inside here. It can be anywhere as long as it is inside. It is between the lens and the F. Okay, we call it U less than F. That is the first position. The second position is when U is exactly equals to F. That is when the object is over here. Okay, U equals to F. And then moving further, we have U, this one is what? Bigger than F, but less than 2F. And then again, we have U equals to 2F. What else? Going further than 2F, we got U bigger than 2F. And we have the last one, U equals to infinity. What's the difference between bigger than 2F and infinity? Infinity is very, very far away. 2F is bigger than 2F, but it could be still somewhere near the lens. Okay, still somewhere near the lens, not as far as infinity. Infinity is like the object is very far away. So the difference is that for U bigger than 2F, usually we would draw the object. Okay, I can draw the object here. So this would be U bigger than 2F. I still can see the object. It's somewhere near the lens. But for U equals to infinity, there's no object drawn. You don't draw any object. You only draw the light ray coming. What light ray? You draw parallel light ray because infinity, parallel light ray coming. If you have the object, then your light ray come from the object, right? You start from the tip here, just like how I drew here. Start from the tip. If it's infinity, then you don't have an object. You just draw light ray. Okay, so total we got 6 position of object. Now, depending on where you place your object, you're going to get different results of the image. That is one unique behavior of the convex lens. Sometimes you will get a magnified image. Sometimes you will get a diminished image. Sometimes you get virtual. Sometimes you get real. Okay, so depending on these different characteristics, there are many applications that you can do with the convex lens. Okay, now take down this one. Remember the 3 rules. Every time you sketch a diagram, parallel focus, center, focus parallel. Pick 2. Just stick to 1 and 2 lah. Just stick to 1 and 2. Sometimes you will notice that 3 you cannot draw. Focus parallel. For example, like let's say the object is too near the lens for U less than F. Like this one. For this object, U less than F, can you draw parallel focus? Yes, right? You join the lens, parallel, and then focus. Can you draw center? Yes, you can join to center. But can you draw the focus parallel? Cannot, right? Because the focus is behind the object, is on the left side. So if you draw focus Then how do you go parallel? You are moving away from the lens. Okay, this light ray, you go focus, you are moving away from the lens. So for u less than f, you cannot use number 3. So stick to number 1 and number 2. Okay, after this, I'm going to show the concave. And after I show you the concave, then I want you to draw a few diagrams, okay? You have your graph paper, right? Or your A4 paper. So I want you to draw a diagram, and you have to really go and practice draw. Only you know how to draw in the exam. Okay, let's go to the concave lens. Drawing ray diagram of a concave lens. Let me erase this. Okay, for concave lens, nothing has changed. It's the same thing. Same rules. Parallel focus. Number 2, center. And number 3, focus parallel. Same rule apply, only a little bit different. Why that's different? Remember the 4 diagram I showed you earlier? The 4 diagram of a concave and the convex, how their focal point behave. One is converging, one is diverging. The difference is there. Okay, now let me show you how to draw it. Number 1, when you're doing concave lens, first parallel focus. Okay, parallel focus. Do I join to the focal? Do I join to here? No. If I join here, then that will be a convex lens. That will be a converging lens. So because the light has to diverge, so this light ray, I will draw it diverging like this. Diverging like this. Put the arrow like this, like this. Now here's a question. If it's diverging, then how does it go to focus? Since I must go parallel and focus. How does it connect to the focal point since it's moving away? So that is why I have to extend it backwards. I have to use extrapolation. Extrapolate this light ray. And it will appear that it is coming from here. So we can also say that this light ray is parallel focus. Okay, you see the difference? The difference is there between a concave and convex. And this is actually the diagram, one of the 4 diagrams earlier, right? So diverge and appear to come from this point. Now it's the second one. Center. From the tip through the center. Like this. And the last one, focus and parallel. Okay, this one a little bit tricky. Focus parallel. How do I draw this? If you remember, from the two diagram earlier, this is the concave. One is I have parallel and then diverge. Correct? And then they are from this point. The second diagram is the second behavior of the focal point is that I reverse these two. I reverse these two. Look at the green arrow. This incoming light ray is directing towards the focal point and then passing through the lens become parallel. Again, the incoming ray which are diverting, the incoming ray which is directed to the focal point, they will become parallel after passing through the lens. So I'm going to draw here. I have a light ray that is directing towards the focal point. Let me put it somewhere here. Oops. Okay, like this. Let me adjust a bit. Okay, I have incoming ray that is directing towards the focal point. Okay, I use a different color. This one. Just a bit, because I'm not drawing according to the scale. So if you draw according to scale, you should get a better looking diagram. Okay, so the light ray that is directing towards the focal point will become parallel. So here they become parallel after passing through the lens. Notice that the blue ray, number 3, this one, is actually this one. Incoming, directing towards the focal point, become parallel. This one, we can also say it is focus parallel. Focus parallel. Okay, now, because our light is receiving the orange one, our eye is receiving the orange one, so we trace it back. That's why we have the dotted line backwards. Same reason, our eye is receiving the blue ray, so we trace it back. That means we extend backwards. What do you see? They meet at the same point. If I extend this one, they meet at this point here. All 3 light rays meet at the same point. That means that is the location of our image. So how do you draw the image? This is point, the tip is point A, the tail is point B. Here, all the light come here. That means this is point A because it's coming from point A. And then the tail is again on the principal axis. We have our image like this. Now, actually, this one you should draw dotted line because you remember, if your image is not the same side as the eye, that would be a virtual image. Same side as the eye, real. So that means this image, eye, our image is a virtual image. This is object. Okay, object is always real. Can you have a virtual object? Is object always real? Can it be a virtual object? I'll show you one example later where we have a virtual object. Okay, but until now, remember, the image not the same side as the eye, it is virtual. Now, why we don't use like left hand side, right hand side? Why we don't stick to, if it's left hand side, then it's always virtual. Now you have to be careful with this one, because if I flip the whole thing, if I take the eye over here and my lens is over here, That means the object is over here. The left-hand side becomes the right-hand side. Then it changes, right? Where is the real? Where is real region? Real is become the left side. This is real because same side as the I, and virtual is on the right-hand side over here. Okay, so use the I as your reference. Okay, you either use the I or you use opposite to the object. Okay, 3 characteristics again of the image. Three characteristics of the image. Number 1, diminished. Okay, becoming smaller. Number 2, what happened? This one is upright. And number 3, it is a virtual image. This is the characteristics formed by a concave lens. You will find that no matter where you put your image, no matter where you put your object, it can be u less than f, between f to f, or bigger than 2f, you'll find that they are always the same result, which means it is always diminished, always upright, always virtual. When you draw the ray diagram later, knowing is not enough. You have to be able to draw it and show it, because that's how you get the marks. Okay, it is true 80% of the marks is from ray diagram, yes. Okay, and in the XPM also, and also from calculation lah. So here, remember the ray diagram. How do I draw the 3 rules? How does it apply for a concave and a convex lens? There is a subtle difference between them. There's a small difference between them. Okay, now I'll give you a little bit of time to draw the image. Yes, in class right now. Okay, now I want you to draw for a concave, for a convex lens. You draw u less than f, u equals to f, u between f to f, u equals to f, u bigger than 2f, and u equals infinity. How many diagrams for a convex? 1, 2, 3, 4, 5, 6. You should have 6 ray diagrams for a convex lens. For concave lens, I only want you to draw 3. U less than f, u between f and 2f, and u bigger than 2f. Only this 3 is enough. Okay, only this 3 is enough for a concave lens. So how many diagrams in total? 6 from the convex and 3 from the concave. You should have total 9 ray diagrams in your graph paper. So take out your graph paper or a piece of paper. You do 2 rows. One is on top, one is at the bottom for 1 page. Okay, so 1 paper, you got 2 pages. You will have 4 ray diagrams on 1 piece of paper. Okay, so you need like about 3 papers lah, 3 graph papers. One is on top, one is at the bottom, and at the back also the same, top, bottom, top, bottom. Now, after you finish drawing, you send it to me and I want to check the diagram. Now you have to really go and draw it. You have to go and draw it so that when the exam comes, then you know how to draw. Okay, you have to test to draw it first. So you draw all these diagrams, and then we will do a table, okay, showing, okay, this one, what is the characteristic of image? You write down the characteristics of the image beside for each ray diagram. Only the 3 Is it upright, inverted, real, virtual, or diminished, magnified for each diagram that you drew. Now, when you draw, if you're having any questions, having any problems, let me know and I'll show you how to draw it on the board here. Okay, so take a screenshot of this and I will move to the graph paper. Okay, I just show you how to set up the diagram. Okay, I want you to only mark down this one, the one that I asked you to draw, this one. Okay, U less than F, U between this one, U more than 2F. Okay, let me go to the graph paper. Okay, the scale to use. Now you can use like this. If you are using a graph paper, then you use like 1 and let me see if I can switch the scale. Wait, I cannot switch the scale. Okay, never mind. I would use, okay, we use like this. We use 2 boxes. We use 2.5 boxes up and 2.5 boxes down for the dimension of the lens. Actually, you can use any dimension you like lah. Just I feel like this is the one that you get the perfect diagram in terms of the scale, not too big, not too small. Okay, if you use like 2.5 boxes up and 2.5 boxes down, meaning that total 5 boxes for the top to bottom for the lens, and then you can use a focal length of 2 boxes. 2 boxes is your F, so 4 boxes would be your 2F. 2 boxes here would be your F, 4 boxes would be your 2F. Okay, you duplicate this for 9 graph because you're going to draw 9 diagram, right? 9 diagram. And then your object height, you can use 1 box like this, 1 box. This is U less than F, U less than F, and then for U equals F, U between F to F, and over here U equals to 2F and bigger than 2F. Okay, so this is you set up your diagram like this. If you use a graph paper, easier, you can use the boxes. If you use a piece of paper, doesn't matter, you can just measure using your ruler. Maybe you take 2 or 2.5 cm for the focal point. And the height, you can take like 4 or 5 cm. Okay, depending on how you want. Just make sure your diagram is not too small and not too big. And it can fit in 1 paper. Okay, 2 diagrams fit in 1 paper. 1 page. I mean, yeah, 2 diagrams fit in 1 page. For the first one, you might want to adjust a bit. For U less than F, you might want to adjust a bit, meaning that you might want to take longer focal point. You can take like 4 boxes. For U equals to F, you can take 4 boxes for the focal point. And then you might want to shorten a bit the height of the object. So the height You can take like half the size of this. Why? Because sometimes you'll find that you cannot join the light ray. You cannot get this intersection. So if you cannot get the intersection, then you adjust a bit. Okay, so make sure that your light ray, they must intersect, because you want to find where is your image, right? You want to find where is your image. So sometimes because of the scale, you cannot find intersect. The line does not meet. Okay, so for you less than f, maybe you want to switch a little bit. You have to adjust a bit. Okay, depending your graph paper lah. Some has a smaller graph paper, some has a more boxes one. Okay, so you try to sketch it, and once you are done, send it to me. Okay, we'll continue to the second half later. After this, I'll give you like a few minutes, like 15-20 minutes or 20 something minutes. Okay, so depending on your progress. So any question, let me know here. I will be here. Okay, let me know in the chat. In the exam, if they if they ask you to draw, they will give you graph paper. Yes, you have to draw according to scale. If the question say only sketch, then you do not need to use the scale. They only want to see how you draw it. Okay, so drawing you have to use true scale, and they will give you graph paper in the SPM. Even if you sketch, right, you also have to make sure your focal point is equidistant from the lens. Like even when you only do sketching, so your focal point also must align. What is the line here? What is the length here? And same length over here. Otherwise, your diagram will look a bit distorted and not the actual answer. For U equals to F, convex lens, how do you draw? U equals to F. Over here, so object. So we have parallel focus. And then we have center. What do you notice about the light ray? Like this, like this. You see that the light ray, they parallel, right? So that means they never meet. Now, the way I do it is I extend this light ray and also this one. Yeah, check. Wait, okay, extend like this, showing that they will not meet. So what happened to the characteristic then? Is it virtual? Is it real? Okay, we are seeing it from here. Image is formed. The light ray never meet. That means they are formed at infinity. Okay, image is formed at infinity. That image characteristic would be, first is virtual. It is on the left side. Second, it is magnified. Okay, it is magnified. And it is upright. This is for the second one, U equals to F. If your object is placed at the focal point, you get infinity image. And this is also true for the first two diagram of the convex lens that I showed you, right? You have focal point 1, you have focal point 2. What happens if the light is coming from this focal point? What happened to the light coming from this focal point? On a convex lens, it becomes parallel, correct? So the light becomes parallel. So that is why when you put the object at the focal point, you get parallel light ray. That is infinity. So your image would appear as if it is very far away. So this is for U equals F. Okay, now you remember to draw the arrow for the light ray. Yeah, you forgot to put the arrow. And for object on 2F, actually it should be, the image should form at the other 2F also. So this is the object and this image. If you place the object at 2F, then the image would be formed on 2F also. And they are the same size, same size. Ah, yeah, the rest is good. Okay, the rest is okay. Okay, the rest you send me when you finished. If you want me to check, then send it to me. I'll give it back to you. Okay, we still have half an hour. Now I want to continue to the lens formula. Normally, how would the question be asked for the ray diagram is that they will give you like an objective, they give you a few ray diagram, and then they say, okay, choose the correct one. That is one way. And also they will ask like, state the characteristic of image if the object is placed at u less than f, something like that. Okay, so without memorizing the table, in your reference book, in your textbook, you know how to sketch, so you can sketch it on the spot and you can tell what is the characteristics of the image. So these are typical questions that will be asked in the exam. Okay. All right. Now, guys, we continue a little bit more on the thin lens formula. The sketching, if you haven't finished, stop it for now. You can do it at home later. And when you finish, you send it to me. I will give it back to you after I have a look at it. Okay. So now, thin lens formula, calculation part. Now, in general, there are two methods to find the characteristics of image. We have just learned the first one, graphical. That means you find the characteristic using graphical ray diagram. The second method is using calculation. Okay, the calculation, the formula of lens. Whichever method you use, okay, no matter which one, you will arrive at the same result, just depending on the question, what they want you to use, which method to use. So here, again, we will do the calculation to find the result of the image characteristics. Now, first, let's look at the formula. 1 over f equals to 1 over u plus 1 over v. The formula is actually very simple, not that complicated, but the confusion part is the sign of the formula. Now, you want to pay attention to this one because when you miss one thing, then the whole thing becomes confused. Okay, so I want to make it very clear that the sign convention of the formula is very important. The value you just put in very easy, but the sign is often people will confuse or careless mistake because of the sign. the first thing, let's look at what is f. F is focal length in meter. Okay, now you can do in cm as well, but you just have to make sure all in cm if you do it in cm. Okay, so f is the focal length of the lens, u is the object distance from the lens, and v is the image distance from the lens. Okay, so the distance of image and object, always we are measuring parallel to the principal axis. This distance is u and this distance is v, always parallel to the principal axis. Now, the sign for the focal length, if we are applying on lenses, again, mirror is different. Next week, I'll talk about mirror. Okay, lens, only for lens, this one. The formula for lens is if you are dealing with convex lens, okay, it is a positive focal length. If you are dealing with concave lens, then you have a negative focal length. Okay, so positive is convex lens, concave lens is negative. Mirror is different. Okay, we'll talk about, we'll save it for next time, mirror. That is the sign for F. For U, now, U actually the easiest because it's always positive. Okay, this one is always positive. Object is always positive. Is it possible to have a negative U? Actually, yes, but very rarely they will ask. And I will show you one example when there's a negative U. Okay, but for now, whenever object is placed at the left-hand side, it is always positive because you always draw your ray diagram, your object over here, and then your eye over here. Okay, it is always positive here on the left side. So object always positive. Now, the last one, V. V depending on, is it the same side as the eye or is it not the same side, the opposite to the eye? If V is the same side as the eye, same side as eye, what do we use? We use, same side is real or virtual? Same side is real, right? Real image. Over here, real image. Here is virtual. Virtual image. So if it's real image or if it's same side as the eye, then we use a positive. Okay, positive. Positive. And if it's opposite to eye position, then it's a virtual and we will use a negative. Get the sign right, you put in the value, you get the answer. Okay, now how about for a concave? Oh, we just talked about concave, right? So concave, it's the same. No, regardless of convex or concave, the U and V follow the same rules. U is positive. Okay, for a real object, we say a real object. Real object. That means always opposite to I. It's a positive. So the V depends. Is it same side or the opposite side? Plus and minus. Okay, so now the lens formula, UV, only tells you the position of the image here. Depending on your calculation, let's say you get V equals to positive 6 cm. What does it mean? That means the image is at 6 cm, positive, right? Positive is right side, so 6 cm to the right. It means your image is here. Measured from the center, you get 6 cm. If your V, you get negative 6 cm, then your image is on the left-hand side here because negative is virtual over here, 6 cm. So without drawing diagram, you know the position of the image. If you were to draw a diagram, you will also get the same result. So it's different method, but same result achieved. This is using calculation. Okay. Now, the U and the V tells you the position of the image. okay? The position, horizontal position. Does it tell you whether the image is magnified or diminished? No. So we need another formula to determine whether our image is magnified or diminished. And that is why we have linear magnification. Linear magnification formula, that is M equals to negative V over U. This is the general formula. Again, the V is the distance of the image. Whatever is the distance of the image, you put it in. If it's -6, you put -6 inside. That means you will have two negative become positive. So the sign also you have to put in it. So whatever value that you get for V and U from your lens formula, you put it in the magnification. And if your M is less than 0, that means it is a negative value. You calculate, you come up with a negative M, then that means this is inverted. Inverted, and if your M is a positive value, then it is an upright. Use the sign to tell you whether it is inverted or whether it is upright. The sign of the magnification, very important. For example, you get M equals to -2. What does it mean? -2, minus, so that's inverted. You know your image is inverted. What about the 2? The 2 means that the image is twice the size of the object. Okay, so if it's an integer, a whole number, it means it is magnified, become bigger. How many times? If you get a fraction, like you get M equals to -1/2, what does it mean? First, it is inverted. 1/2 means it becomes smaller. Fraction, right? Fraction, it becomes smaller. That is diminished. So image is half the size of the object. Let me write this down. Inverted, image twice the size of object. This is inverted, image half the size of object. What about M equals to 3? So this is positive, right? So it is upright. And image is 3 times size of object. You can get from magnification. So magnification tells you the orientation, upright or vertical, and the magnification. The thin lens formula tells you the horizontal position. Okay, like that. Now, why do we call it linear magnification? Linear means one dimension. So for example, if I have a lens here and my image has a height of 2 cm, linear, one-dimensional length, meaning that there's just length, not area. If we are talking about area, that would be 2-dimensional because you have length and width. So we cannot calculate the magnification of area. That, for example, if I say that our object having an area of 2 cm square, can we calculate the magnification of this area? We cannot calculate because area is a 2-dimensional. Okay, but here understand that we are dealing with linear magnification, only length in 1 dimension, just the height. Okay, just the height. So that means whatever image that you get, let's say 4 cm, we only compare 1 dimension length, the height. We only compare the height. Okay, so it's linear. So if you compare the height, this is 4 cm, this is 2 cm, how many times? 2 times greater. So the magnification is 2. Magnification is 2. If the image is 1 cm, then magnification is 1/2. Okay, only the height. So I can also say that my magnification equals to size of image divided by the size of object. Here you get your second formula. By size, I mean the height. Okay, the height. Usually you are given height all the time. So the height of the image, you divide by the height of the object, you get the magnification. Formula number 1, formula number 2, and plus the thin lens, you have 3 formulas over here. Now, one thing I want to make clear, because some students, okay, they are a bit confused. Why there's a negative in the magnification? In your reference book or in your textbook, sometimes you will see that the magnification does not have a negative, only V over U, like this. Why sometimes got negative, why sometimes don't have negative? Okay, for those that does not have a negative, like M equals to V over U, meaning that they should have a graph to tell you whether it is upright or inverted. Okay, so meaning that when you draw the graph, you found that, okay, the image is inverted. You already know that it's inverted, so you don't need the sign to tell you, right? You don't need the sign to tell you. You already have the ray diagram. Okay, it's inverted. I can see it. Then I put in, when I calculate the magnification, so I don't worry about the sign anymore. I just put in the value of V and the U. I just want to know what is the magnification. So the negative does not bother me because I already know whether it is upright or inverted. Okay? But the general formula of magnification is it has a negative. Okay? So let's say you're not drawing any diagram. You don't know whether the image is upright or inverted. So you have to use a negative. You use a negative, that this negative, you found it, it will tell you whether it's inverted or upright. Okay? It's kind of like a similar example for force. If I write force equals to -5 Newton, you can already imagine that, okay, this force is pointing to the left, right? Pointing to the left, 5 Newton. This is one way to write it. I just write it mathematically, -5 Newton. Or I can write my force, I can show the direction. I show the direction and I only write down the magnitude, 5 Newton. F equals to 5 Newton. The negative is already represented graphically. That is the difference. That is why sometimes you see negative, sometimes you don't see negative. Because without the negative, we are only calculating the magnitude. Okay? So with the negative, you can get the orientation. Upright or inverted. Okay, now I'll show you one example on calculating using the lens formula and the magnification. Okay, let me go to the next slide. Okay, example number 1. Determine the position and magnification. So we have position, we have magnification of the image formed by a convex lens of focal length 0.2 when an object is placed 0.3 meter from it and 0.15 meter from it. Okay, let's do A first. Now, depending on what method you want to use, you can use a drawing. Yes, no problem. You can go ahead and draw it. But here I will show you how to use the calculation. Method number 2, formula. Okay, so first I write down what is my object position. My object is placed what? 0.3 meter from it. So remember our object, what is the sign? We always take a positive, right? For a real object, 0.3 meter. What is my V? I don't know the V. What is my F? What lens is this? Convex lens. What is the sign? Positive. So it's a positive, what? 0.2 meter. Okay, do the 1 over f equals to 1 over u plus 1 over v. So 1 over 0.2, 1 over 0.3 plus 1 over v. Calculate this, you get 1 over v equals to 5 over 3. Be careful, this is the reciprocal, so I would flip this one. I get v equals to 3 over 5. That is positive 0.6 meter. Now you don't have to write the sign, I write it just to show you, okay? Just to show the difference between negative and positive. So v is a positive 0.3 meter. What do you know about this? That means my image is positive, means to the right, right? Right side, somewhere here, 0.6 meter. So it's a real image. And 0.6 meter from the lens. And it is at the right side. Okay. How about the orientation? Upright, inverted, diminished, magnified. Then we do the magnification. M equals to minus V over U minus plus 0.6 over plus 0.3. What do we get? We get minus 2, right? Minus 2. That means my image is inverted and magnified. 2 means twice the size of the object. Here I got all the information I needed. Magnified, inverted, 0.6 meter from lens, real image. The characteristics all are there. Even if you want to draw, okay, you can draw it. Now you draw it like this. Here's your convex lens. You have your principal axis. Here, okay, then you have to know lah. Let's say I use 0.2 is the focal length, right? Focal length 0.2. So where is my object? My object is placed 0.3. So that is, if f is 0.2, 2f is 0.4. Okay, this is 0.2, this is 0.4. 0.3 is somewhere in the middle. So that is u bigger than f less than 2f. Okay, then you have to roughly measure this one the same distance. Otherwise, you get a different answer. You have to make sure that your focal length is the same distance here. And you have 2f over here. Then you do the sketching, right? Parallel, focal. Okay, parafocal, and then like this, center. Like this. Okay, let's say this one to join here. Then you have your image like this. Okay, then you can see lah, inverted, magnified. How far from the lens you can measure? This is 0.2, this is 0.4. Okay, then you can measure the length over here. If you're doing this graphically, you can measure here. Then you can get a distance from the lens. You can even measure the magnification. You measure the height of the object. You measure the height of the image. You divide it, you get the magnification. You will arrive at the same result. Same result as if you use the calculation. Which one is easier? Up to you. Okay, you can use calculation, you can use graphical. B. Again, does my U change? No. U is positive 0.3. Again, I want to find V. Oh, sorry, my U changed, right? My U is 0.15. 15 meter. And my f is same, positive 0.2 meter. So I do 1 over 0.2 equals 1 over 0.15 plus 1 over v. I get 1 over v equals to negative 5 over 3. V would be negative 3 over 5. Negative 0.6 meter. This is what? This is virtual left side. 0.6 meter from the center of the lens. Okay, find the orientation. Put it in. M equals to minus V over U. M equals to minus 0.6 over 0.15. So these two become plus, right? So plus 0.6 divided by 0.15 plus 4 means what? Upright. Magnify. What is the magnitude of the magnification? 4 times. There go your 3 characteristics. Upright, magnified, virtual, and 4 times magnification. All you can find using thin lens formula.